All right, here we have a velocity versus time graph, and we want to find two values from it. The first is the acceleration. Now you may remember from position graphs, the slope of a line usually tells us something about it. So if we look at the slope of this, what we can do is say, all right, slope is rise over run, and so once again, the rise is in units of meters per second, and the run is in units of seconds. So if you do meters per second over seconds, what do you get? Hey, you get meters per second, or meters per second squared, which, hey, that's an acceleration. So the slope of a velocity graph gives you the acceleration. So to find the acceleration of the object, we simply have to find 2 points. So maybe this beginning point and this end point, and find the slope. So let's see, the slope is, the rise is it goes from 40 to 20, so that's a negative 20 meters per second. And the run is it goes from 0 seconds to 8 seconds, so that's 8 seconds. So then we're just going to do 20 seconds, or negative 20, meters per second over 8 seconds, and that's going to give us our acceleration. So negative 20 over 8, I get negative 2.5. So the acceleration is negative 2.5 meters per second squared. And that was simply the slope of the velocity curve, much like we found the velocity from the slope of the position curve. Now, this is the one that's a little more tricky, the displacement. So you might remember the units of displacement are meters. It's like position. So how can you get meters out of units of meters per second in seconds? Well, the other thing besides slope that's important is the area under the curve. The area under the curve refers to this area underneath this line and trapped by the x-axis and y-axis, this area all here. This area under the curve actually has significance. And if you look at the units, if you were to find the area here, there's meters per second times seconds, which gets you units of meters. That is the displacement. So the area trapped under this curve actually tells you how far the object has traveled. It's kind of interesting in that way. So then the question is, okay, how do we find the area under this curve? So there are several ways to do this. The first way might be to simply divide this area into two regions, one being a rectangle and one being a triangle. So in other words, I can start by saying, all right, I know that this area right here, this rectangle, is simply the length times the width. So the length is 20 and the width is 8. So this area here, 20 times 8, is 160. So that's this region. And then I can find the region here. This is a triangle, and the area of a triangle is 1/2 the base, so from here to here, which we said was 8, times the height. So from 20 to 40 is 20. So if I multiply that out, I get that is 80. So 80 plus 160, adds up to 240. So the displacement is 240 meters, meaning this object will be 240 meters away after traveling for 8 seconds. Another way I could find the area here is it's kind of a think outside the box type question, is you say, okay, this thing started at a velocity of 40 and it finished at a velocity of 20 over these 8 seconds. It had uniform acceleration the entire way, meaning it did not change its acceleration. It was decreasing by the same amount. So the average velocity over this period is 40 plus, it's the average of 40 and 20, or 30. This is the average speed. So you can almost think of it as traveling the same speed the entire way, 30. And so then it's simply 30 times 8, which, hey, is 240 meters. So any way you can think of to get the area under this curve will tell you the displacement of the object. Notice that the area is a positive value because what direction is this object traveling? It's got a positive velocity, so it's traveling to the right, so it has a positive displacement, meaning it is now 240 meters away from where it began. We'll do some more of these in the next video to get some more practice, but this is just one example of this. So until next time, I am Derek Genova. Have a delightful day.